We having a open session now, discussion for the whole afternoon?
Yes.
Okay,
So I think that our group photo is supposed to be at 6 p.m. So we're gonna have to make this a little abbreviated.
okay. I guess all speakers virtual for both sessions and physical speakers come up to the front. Okay. And Paul, can you see questions online or who sees the questions online?
Yeah, I'm checking the questions online.
Okay,
At the moment, we don't have any in the chat, but for those joining us online,
we have a line forming in the room though, so.
okay, then.
Hey, Paul, my question was actually going to be for you. Great model. I really like what you're doing there. Have you considered incorporating a more realistic grain geometry into your model? And sort of the second follow-up question to that is if you are able to simulate the grain charging in that at all?
For the first one, yes, we are about to start working on doing more realistic grain models. I mean, we tried for one publication that we did some variations of the spherical shape, and it didn't make too much of a difference. It seemed to be very much governed by the porosity. But it's definitely something that we aim to do. About the grain charging, that is more of a challenge. It would probably be doable with some extra effort, but at the moment we don't have any, or we haven't considered this so far.
I had a question for Tom. It's on. I had a question for Tom. I'm just wondering, are you planning to do any kind of cross section through the regions where you think you have different shock pressures?
Yeah. Yes. Yes, this was the very first pass through this. Yeah, this is the very first pass, and what we did was we actually just took flakes that came off, and then we mounted them, and then took the spectra. Actually, Alicia has now figured out how to do these fib lift offs, and it's going to be a much more controlled process. And so we're working together to basically do a fib lift off, so we have really good control.
Okay, yeah, it'd be cool to see a fib cross section through what you've, nano IR mapped. It'd be awesome.
That's the plan.
Oh, so you're supposed to be here. Okay.
Toji from Georgia Tech. I have a question for the first speaker of space weathering. Anastasis, am I right? Yeah.
Hello.
So my question was, how do you characterize the thermal condition, particularly heating part? I was wondering, like, how you calculate the heat in your simulation.
So we used the velocity of the atoms and then used some equations to basically get the individual temperature of each atom.
So basically, are you tracking like entropy?
No, we're tracking the velocity and then I forgot the equation that we used. It's basically one equation that converts the velocity to the temperature.
Okay, understood. Thank you.
Can I follow up with a related question? So Brandt mentioned this, the recombinant desorption threshold temperature drops considerably if you have magnesium and iron and a lunar material. Does that matter in your case? Because you used a pretty high temperature.
Is that a question for me?
Yeah, that's for you.
Sorry, can you repeat it?
So the recombinant desorption temperature you mentioned was 600 to 700 Kelvin, which is true for silicate. But if you look at a lunar sample, that can shift all the way down to 250 Kelvin, depending upon what's in the material. Does that have any bearing on your yields and kinetics?
It should, but we used the SiO2, so we only saw recombinative desorption at very high temperatures, and in yeah, so desorption and ejection we saw at very high temperatures.
Yeah, pictures, no one's forming yet for pictures, so we still have time for more questions.
My question is actually for Autumn. So really interesting the work that you guys were doing. I love that you were able to show such definitive changes in the spectrum, but I was wondering if you had done any measurements of the compositional changes to the materials and maybe what that looked like.
So that's where the TEM is going to come in. So we're working on doing fib sections right now so that we can do TEM and do EDS and EELs and all of that kind of stuff so that we can get that compositional information.
Can I ask a question?
No, yes, of course you can. Absolutely. All questions allowed, everybody.
Okay, I want to ask a question for the young lady from Canada.
Her name's right on the screen.
Fatima?
No.
Amanda?
Amanda, yes. Sorry. So what I'm thinking is you have other volatiles besides sodium. So how can you have a monolayer of sodium if you have other stuff like sulfur or, I mean, there's other volatiles and people have hypothesized, I mean, well, that there's obviously sulfur and it's also going to be migrating to the poles. So what does the presence of these other volatiles have on the adsorption? I mean, how can you form a monolayer of sodium if you have other stuff sticking on the surface as well?
Right. That's a good question. So right now I'm just focusing on sodium as like the extreme. But of course, as you said, there's other volatiles on the surface. And so that's definitely something in the future that would be very interesting to model as well. Not just one volatile, but multiple volatiles and how their interaction between each other as well affects the SBE.
Yeah, I have no idea what the answer is. That's why I want to know if you know the answer. Thanks.
No, not yet, but definitely something we're looking into as well.
Right. Do we have any online? Any more questions online?
No, not at the moment.
Okay.
This is a question for Brandt. In your results maps,
Yeah.
I have a sort of a general, not very well formed question.
Okay.
But there's a lot of variability that I could attribute just to sort of essentially the statistics of the Monte Carlo sampling. But there was also a lot of kind of macroscopic patterning, which I just didn't understand, at all. Like, can you make any general statements about why those maps wouldn't be smooth? Why there would be sort of striations versus latitude, for example?
Yeah, I think that just has to do with the fact that I was averaging those out, right? So in order to speed up the calculation, I was not sampling every point, right? And so I would kind of skip some points. And so you'd end up with like kind of this bend here, and then I was interpolating it out.
Okay.
So that probably is just.
So they may just be artifacts.
Yeah, it's probably just average.
Okay, yeah, thanks.
Hey, so this is Hopi Shi from University of Hawaii. Toshi, I just had a question. So the mass wasting argument is really convincing that's definitely overturning a lot of depth. But I was wondering whether, on the other hand, you could just argue that you take longer to develop enough hematite to get the signal that's observed. What is the thinking on that?
Maybe on.
Yeah, so this is a great question. So definitely in terms of, like how we can keep the hematite for a long time, that is something like we are considering. So according to Shuai's paper, first of all, they need oxygen. And on the other hand, impact would also help developing hematite as well. So this competition must be considered definitely in the model. However, the issue is distribution of hematite. Those are actually located equator and eastward, east facing side of a high topographic high. That is a very critical constraint to argue impact is important, contributor. We need to consider the direction of the earth. This is sort of like a very entangled problem, which we need to answer a little bit. But at this point, I don't have any idea on this. So if you have any opinions, please let me know. So.
Thanks.
Question for Brant. Just wondering in terms of like solar proton events, how would that affect the formation of water and hydrogen? It's part one of the question. Could we measure that? And then I have more of a harebrained question after that.
Yeah, so what I did in those simulations was just like an average storm, right? So if there's a big sporadic event, there's probably going to be a spike, which would result into a kind of this spurious event, maybe not instantaneously, but later on, right? Because it's a diffusion limited process, so there's going to be some amount of time lag for that to actually kind of propagate through the reaction.
My other question then would be, what if you have a really extreme solar proton event, like a Miyake event? Something like that. Would you be able to see like expressions of that, like buried? Just thinking, it's harebrained question because we don't really know what they are.
I would probably speculate that you would end up forming more of these hydrogen vesicles than you would water, right? Just because you're dumping so much protons in there so rapidly that it's going to potentially go to H2 and not OH, which then would again be the diffusion is so slow that if you dump that many protons in there, it's just going to go probably predominantly hydrogen.
Thank you.
Yeah.
Actually, sorry.
Can I? Brent, I have a comment on your work. First of all, this is definitely exciting. At the same time, I want to address, this is like we had a conversation before, but impact melting is just a part of water formation. When it comes to temperature increase, not only impact melting, also heated material would be able to release that. This is from your theory, recombinative dissociation. That would be something affecting additional water release. So you can definitely consider that would be impact melt would be giving just lower bound of it.
Yeah, that's a very good point. It is a very lower limit, right? Because like Toshi said, these impact events are going to create a thermal gradient around that, which would cause more recombinant absorption, not just the area that was melted, which is what I was really only considering here.
Yeah, we don't have the full volume element, nor do we really have a shock wave in it, right? Just a delta T or some rigid range.
Right, which is, work to be done at some point.
I guess my question is actually really similar to that, because you mentioned that as you implant, you're going to build up, the terminal bonds, and you reach saturation, you start to outgas the hydrogen. But what is the refresh rate of those surfaces due to the micrometeorite impacts? Because each one of those impacts is basically going to reset the amount of hydrogen that's trapped in that surface.
Right. So you're definitely going to lose some amount. I don't know exactly what the fraction is, but in addition to that, you're going to have overturning, which is what Toshi does. I mass balanced it. I didn't really calculate the percentage that was lost during an impact event, but I would say that just given the relatively low flux that is occurring, it's at most 10 to 20% of the surface that you're losing.
Yeah, Harvey, one last question before we call the night.
Thanks, Carl. I have a question for Sean. So in your lab experiments, it looked like you had the solar wind coming straight down into the lava tube. Does the angle make a difference? Like, so if this was like a lava tube at a different latitude, like, would you get different results?
Yeah, so the angle definitely does make a difference. I've done like a test on that. It kind of goes as you would expect, just pretty much by the cosine of the angle. The main thing is that the CSWE, when it produces its ion beam, it produces it not in a completely collimated straight beam. It has a slight divergence to it. And so that's why there's a slight difference between one ion going here and then one ion slightly next to it. It'll have a slight angle comparatively.
Thanks.
Yeah.
Okay, well, let's go ahead and wrap up the combined session and thank all of our speakers once more.